You know, we throw around the words heat and temperature all the time, pretty much interchangeably. But do we really know the difference? Well, it turns out one is the cause and the other is the effect. And that little distinction, it explains everything from how a thermometer works to why a tiny little spark actually has a higher temperature than a massive iceberg. So, let's dive in and unpack the physics of what makes our world feel hot or cold.
It all kind of starts with a question you've probably asked yourself while looking at a weather report from another country. How is a beautiful, warm 25 degrees in Paris a freezing temperature in New York? It's the same physical reality, but we describe it with totally different numbers. So why? Why are there so many different ways to measure the exact same thing?
To answer that, we first need to get to know the main players in the world of temperature scales. First up, we've got the Celsius scale. This is the one most of the world uses, and honestly, it's just so elegant and simple. It anchors itself to water, setting its freezing point at a nice clean 0 degrees and its boiling point at a perfect 100. Easy, right?
Then there's Fahrenheit, where water freezes at 32 and boils at 212. Now, the numbers might seem a little, well, random, but it's the standard in a few places, most famously in the United States.
Okay, now for all the science folks out there, there's the Kelvin scale, and this one is a big deal. It's the absolute temperature scale. Its 0 point, absolute zero, is literally the coldest anything can possibly get. It's the point where there's zero energy. And you'll notice we don't say degrees Kelvin, just kelvins.
And just for fun, to show you how many ways we've tried to crack this nut, there are even old-school scales like Réaumur. Here, water freezes at 0 but boils at 80. It's really just a curiosity now, but it shows you that for centuries, we've been trying to find the perfect way to measure the world around us.
So, we've got all these different temperature languages. How in the world do we translate between them? Well, lucky for us, there's a kind of Rosetta Stone that makes it all make sense.
And here it is. This one beautiful formula is the key. It's our universal translator. By setting these ratios equal to each other, you can convert a temperature from any scale to any other. It works because it mathematically lines up the fixed freezing and boiling points of water across all the different systems. It's pretty genius.
All right, now that we have this awesome tool, let's have some fun with it and solve a classic temperature brain teaser.
Okay, here's the big one. Is there ever a point where the number on a Celsius thermometer is the exact same as the number on a Fahrenheit thermometer? A moment where they just agree? What do you think?
To figure this out, we just pull out our conversion formula. So as you see in step 1, we start by just assuming the Celsius and Fahrenheit values are the same. We'll just call them x. For step 2, we just pop x into the C and F spots in our formula. From there, it's just some straightforward algebra. We cross-multiply to get step 3, then we get x all by itself on one side in step 4, and boom, we've got our answer.
The answer is minus 40. Yep, you heard that right. Minus 40 degrees Celsius is the exact same temperature as minus 40 degrees Fahrenheit. It's this one kind of magical point where these two otherwise different scales perfectly align.
Solving that puzzle is pretty neat, right? But it relies on something we all just take for granted, that thermometers actually work. I mean, how can a little tube of mercury possibly know the temperature of an entire room? The answer lies in a fundamental law of the universe that has a very strange name.
First, we got to get our heads around this idea of thermal equilibrium. Imagine you place a hot coffee mug on a cool table. What happens? Well, energy flows from the mug to the table, right? And this keeps happening until they both reach the exact same temperature. At that point, the net flow of energy just stops. They're in balance. They're in equilibrium.
So this is how a thermometer uses that principle. Look at this diagram. Imagine A and B are two different objects, and C is our thermometer. If we touch the thermometer, C, to object A and get a reading, and then we touch that same thermometer, C, to object B and get the exact same reading, what can we conclude about objects A and B? That they must be in thermal equilibrium with each other. And this brilliantly simple idea is the zeroth law of thermodynamics. It's called zeroth because it was actually figured out after the first and second laws were famous, but it's so fundamental it had to come first. This law is the very reason measurement is even possible.
So, the zeroth law explains how a thermometer works. It reaches equilibrium. But this brings up a deeper question. What is it actually measuring? It's not heat. And understanding that distinction is probably the most important takeaway of this entire explainer.
Let's break this down. The key difference is what they are. Heat is a form of total energy. Think of it as the sum of all the wiggling and jiggling from every single molecule in an object. Temperature, on the other hand, is a measure of the average energy. It's not about the total amount, just the average intensity.
Okay, here is the absolute best way to visualize this. Picture a steaming hot bathtub full of water. And, right next to it, imagine a single tiny spark from a welder's torch. So which one has the higher temperature? The spark, of course, by thousands of degrees. But which one has more heat? The bathtub. And it's not even close. The tub has trillions upon trillions more moving molecules. So its total energy, its heat, is way, way greater.
So the crucial point is this simple relationship. When you add or remove heat from a system, the effect you measure is a change in its temperature. Heat is the cause, temperature is the effect. That's the most fundamental takeaway from all of this.
So we've seen how the zeroth law gives us the rules to measure the world around us. But that's really just the beginning of the story. It makes you wonder, doesn't it? If the zeroth law sets the stage, what might the first and second laws of thermodynamics tell us about something really big, like the ultimate fate of the entire universe?